Hello, how are you doing? Can you hear me? Am I muted?
Yeah, I can hear you, Mike.
Very good. Oh, thank you so much for your time today. I want to triple check you're okay with me recording this.
Yeah, sure, yeah, no problem.
Thank you very much. I'm sure that many of the people we're going to listening to this they're very interested in your research. Would you prefer to start explaining all of the good research you're doing at the moment, or would you rather hear our interest levels?
Yeah, maybe we can start with yours because I'm kind of working on a different theme of research. So, if we can start, then I can discuss about areas that is more relevant.
Very good. Okay. I'll start just with my background to make super clear. I'm an aerospace engineer, about 40 years experience, a lot of composites experience in aerospace, which of course is not really what we're talking about. And what we're talking about is a project that has nothing to do with my current aerospace employer. It's outside of that. Um, I'm involved with a group of futurists. We've started a group, the Omni Futurist Group. One of our concerns is when and we started I founded the group about a year and a half ago, concerned about when artificial intelligence and robotics supplants most humans in their jobs because they're more cost effective. What are people going to do? And I'm concerned that perhaps the United States doesn't prepare well enough for it. How do you supply them with homes and with food so that they survive until, let's say, artificial superintelligence arrives and is able to, come up with good solutions. Um, Another side note, I was on the board of directors of a artificial general intelligence company here locally in Seattle. I'm an investor in that. So I have lots of interests in that area. Okay. But, as you know, there's a current already problem facing all humanity, one of which is climate change, and the other is economic displacements and homelessness. And so one of my solutions for how people could feed themselves is agroforestry and market farms, small places where you can gather some of the homeless together and give them a place where they could co-house and co-work, feed themselves. And as I'm doing this research in agroforestry, I come across biochar, primarily for the amendment to soil. Okay. I did make some biochar this weekend in my backyard. I've got like 5 acres in the woods out in the countryside, and that was fun. Anyway, once I start going into biochar, then I start seeing other aspects of it. I'm really startled at how much biochar can be used for many different things. And Terra Preta, of course, hit my Googleplex feed of news articles because they know I'm interested in biochar now. And then I start seeing about how long it lasts in the soil. Just really remarkable. As versus, I'm in this forest here and I'm thinking, well, if I plant more trees, carbon dioxide comes out of the air and gets retained. I'm taking some basic classes in whole farm planning. And when I talk to them about, well, I can help sequester carbon by planting. And they said, well, once it dies and then it decomposes, then it goes right back. It's a perfect cycle. So the biochar seems to break that cycle, as we can see with the Amazonian 1,000-year-old whatever biochar. Okay. And so it's very clear carbon sequestration works with biochar. Now, all of the composites that I work with in aerospace, of course, the petrochemical plastics, the epoxies, the fiberglasses, the carbon fiber fabrics, the foam core for sandwich that I've designed, it's all really bad for the environment. So what I've done is I've suggested perhaps use bio-PET epoxies with natural fibers for the face sheets and a foam core that is perhaps something like linoleum with biochar in it. because really what you don't need a whole lot of strength in the core. You're looking for something that's a thermal insulation, a sound insulation, acoustic insulation, plus the ability to hold the two face sheets apart under bending loads, right? That's a normal function of core. And so I've said this might be a possibility. What I'm doing is I'm starting to look at the bioplastic research across the globe. What are people looking at? What fibers could replace fiberglass and graphite? And I come across a few that I'm not familiar with right away. One is jute and one is flax. Now we have one of the members of the group, Dr. Sharif Rana in Bangladesh, and he's the person that I'm discussing jute, cashew nut shell oil as a starting point for epoxies. I'm going to Tulsi is another. There's a two-component epoxy, bio-epoxy that involves cashew nut shell liquids and Tulsi. Eugenol, I believe, is the other, the derived chemical from Tulsi. Anyway, so Bangladesh has a possibility, okay? Now we have another member of the group. She's not feeling too well today, but Alora is in Saskatoon. I didn't look this up because she is a member. I'm looking at flax. You may know, of course, the biocomposite research in flax is mostly in Europe, the French and so forth. I'm going, okay, European flax, probably too expensive. I want local materials, okay, and fabricate it locally and use it locally. Where else do you grow flax? Well, it turns out Saskatoon, Saskatchewan are quite a center for that. When I start researching, I come across Biolin Research. He's working really hard to try to find use for flax straw. I read that you've got maybe 1 million acres, and what do you do with the straw? A lot of it is burnt, which probably isn't good for pollution, carbon dioxide, right? And then I see the flaxseed oil. I'm such a dummy. I told you about jute. I didn't know anything about it. I didn't know what we use it for. Okay, that's burlap sacks. What's flax used for? I don't know. Okay, of course, it doesn't make any sense. It's linen, right? And the oil seeds, right? What are they used for, right? Linoleum. I, as a kid, always thought linoleum was petrochemical. I didn't know it came from seeds. I've never worked with biomaterials, okay? So I'm learning all this stuff. Look at that flax plant, right? You've got the oil seeds that could be a precursor for epoxies, bioepoxies of some nature. You've got the straw there. And then I'm looking at the, oh boy, and now the term is escaping me, the woody stem, the shive.
Yeah.
The shive could be used for biochar.
Yeah.
Potentially, okay? I find a company in Craik, Saskatchewan, Carbon Smart Tech, something like this. They're making biochar there. I come across you've released research on biochar. And I'm going, okay, potential solution for homelessness. Here in Everett, I live in Seattle, I work in Everett. Everett has a company called Pallet Shelter that builds these small homeless shelters made of about 6 composite panels, fiberglass panels with foam. And they come stacked flat, and you put them together in 30 minutes, and you've got electricity, heat, a locking door, very simple construction. It's, at least in the US, the homeless shelters are now converting from these large warehouses where the homeless go to individual shelters made of these composite panels kind of quickly bolted together. They've got heat, they got electricity, they got air conditioning. It's about $11,000 per unit. I'm working with a colleague of mine. Jasmine has started a company, a for-profit company in Everett, and her whole function is to provide services to the homeless. She has connections to the homeless shelters in Everett, to Pallet Shelters, the company, and she herself is a social worker who deals directly with the homeless. So one of the suggestions is that in different localities to come up with biomaterials, biocomposites for these panels, discuss with this company in Everett, Pallet Shelters, are you interested in trying to sequester carbon at the same time you're providing homeless shelter?
Yeah.
Okay. One of the things I think that biocomposites probably struggle with is the prices might be a little bit higher than petrochemical. So you might need a specific type of audience, a specific type of customer who is willing to pay a bit more for the panels in order to do two good things at the same time. Okay. So Alora has said that there is a homeless population in Saskatoon. That may be one location to try to use flax materials to make composite panels to build homeless shelters. And now you've got an environmental situation where you're in, I'm not going to say Arctic conditions, but you have cold weather, right? Bangladesh, I got Dr. Sharif. Perhaps we've got jute, cashew nutshell, liquid oil panels, make homeless shelters there for the homeless in Bangladesh. And now we deal with hurricanes and tropical weather and flooding, right? Completely different environments to work this, local materials, local solutions. So as is typical of me, I've talked for way too long already. I appreciate your patience with this. The first thing I actually wanted to ask you and forgot was, would you please say your last name so I can say it correctly from now on?
Yeah, so my first name is Bishnu, last name is Acharya.
Acharya. Okay,
Yeah,
Dr. Acharya. All right,
yeah,
so
you can
there's my
call me Bishnu. Yeah, that's fine.
Bishnu. Thank you very
Yeah.
much, Doctor. Bishnu, thank you very much for that. So that's my spiel, very quick. We are a startup. We have not actually become a proper business. We anticipate becoming what's usually referred to as a B Corp, but in Washington State is a social purpose corporation. It will be for profit, but with a social purpose, right? That's the goal. We're looking for partners who want to work with us, right? I also would like to go open source on this. There's no point in me trying to. I have a series of patents for aerospace, right? I know what it involves. No, thank you. For this is for humanity and good, not for lining my pocket. Okay, so I'm interested in looking for partners who are interested in open source solutions for humanity, both for carbon capture and for housing homeless. So that's my spiel. I would love to hear about your research.
Yeah, no, thank you for that, introduction. I think it's really good to see, a different angle of, how the biochar can be used, because when we're doing research, we're mainly focusing on materials, but we always try to, see how those can be related to a proper application or a real life application. So I think what you just discussed or explain, I think that has a real good impact. Yeah, so in terms of biochar and biocarbon, we have been working in this area for quite a bit of years now, mostly looking at the biochar from different types of feedstock and characterizing the biochar and looking at what different application it can be used for. We did project in past where we use biochar in wastewater treatment systems. Like we studied like adding biochar as a filler in the wastewater treatment. Um, at a point where the wastewater enters the treatment systems. And we found that, biochar does help in expediting the treatment, as well as it helps in the settleability of the sludge. And if the sludge goes to anaerobic digestion, which is most of the wastewater treatment plant has, then it also helps to improve the biogas yield. And finally, the sludge, with the biochar has a good nutrient property that can go into the soil for, for soil application, like land application. So we use that biochar in that way. The other thing that we did was, we looked at the biochar-based composite material. So as you talk about flax, there is other thing that is growing here as well, which in US is still considers under cannabis, but in Canada we can grow hemp, and hemp does not fall under cannabis. Kind of, they are separate. So at least the hemps are grown as a cash crop, and in Saskatchewan is also doing a lot of hemp farming as well. We get the hemp fiber too. So the flax fiber is there. There is hemp fiber as well. A significant amount of hemp fiber that we haven't. The processor has not found application for that. So there is another avenue as well. In this kind of work, flax obviously has some its own challenge and benefit as well, because it is burned in the field. So if anything can be done with the flax, then definitely it will have that more, obviously the project has its own carbon sequestration, but then since it is burned and released all the pollution that is created, if we can avoid that, then it will look even better in terms of environmental points. Yeah, so flax. So in the project, we recently completed with one PhD student. He was looking at biocarbon adding to hemp fiber reinforced composite materials. Where we use the hemp hurd. So when we say hurd, it's like in case of flax, we call sipes. So hemp we call herds, which is basically the same idea that the hard part of the stem, and then the fiber is going into the fiber application, and we took the hurd and we pyrolyzed the hurd and then used that for making biocarbon, and added as a filler into the composite materials. And then we studied the properties of those composite material, especially all these natural fiber reinforced composite materials. They have issues with the moisture absorption and all those things. And in fact, we use a vegetable oil-based resin for making our composite material. So the composite was 100% bio-based composite. We haven't done the cost part yet, but in terms of property or in terms of making a composite, it's all 100% bio-based composite. Then we looked at the properties, especially it's a water-based property. I'm not sure if I can share the screen.
I think I gotta probably make you a host.
Yeah.
I'm not very good at this system. Everybody has a good laugh at me because I'm not really very good at this. Okay. Hold on a second. Let me give you host. I'm gonna make you the host now. Okay, Vishnu. Okay, you're the host.
So can you see this shared screen?
I can.
Okay. Yeah. So this was the work done by our PhD student Rajkumar Dahal, and we have a collaborator in Guelph University, Dr. Animesh Datta. So we two kind of collaborated on looking at the hemp biocarbon as a filler and hemp biofiber in biopolymer composites. So we all know, as you already explained, this problem of in terms of the linear cycle for all these non-biodegradable or petroleum-based materials, and then the glass fiber, and then the growth of market, the polymer market, or this biocomposite market. There's a big opportunity there, but where the composite is coming from, still it's a question. So we worked with the hemp biomass. Again, it just compares. It just compares the natural fiber and where does it fits into this into this properties table and chart. So this was basically to compare like what the data that we're getting out of our work and where does that data fits into this curve. Yeah, so basically, for the plant-based composite material, the limitation are the moisture sensitivity. It could be low thermal stability, variability, because the fibers they are very depends on, if it is Saskatchewan, you have different quality fiber. If you go Europe, you get different quality fiber. If you go to Bangladesh, you have different quality fiber. So the properties of fiber, it just varies from place to place. So it's difficult to get more consistent product. Also, the durability of that product is also, thing that need to be investigated. So what we hypothesized was if you add a biocarbon, then it adds the hydrophobicity of the into the material. It improve the interfacial interaction and improve the mechanical properties. Also, because if it's already have a good thermal stability, it can increase that thermal resistant, and somehow it can help us to get more consistent kind of material at the inside. There's like a biocarbon is used in a number of different applications. So again, these were mainly the objectives were to study, what was the effect of water absorption properties on the biocomposite, effect of thermal properties on the composite material, and then also the mechanical properties at the end. So basically what we did was we took the hemp herd and then we kind of grind them, got the herd, we pyrolyzed them in a pyrolyzer, we got our biocarbon, then we grind the biocarbon to a fine particle. So these were below 45 microns particle. And then we use that biocarbon in making the composites. So the student who worked on it. So we used the hand layout method for making our composite samples. So basically biocarbon, we got the bioepoxy from a company in Ontario who are supplying that.
Pardon me, you got the bioepoxy from where?
There is a company in Ontario. I can find the name for them, for those companies, yeah. It's not something that is popular. It's just we have to order 2 months ago. And then they were able to deliver that 40, 60 liter that we needed for our work. So but yeah, it's not something that was readily available. So
no, correct.
Yeah, so bioepoxy, we just mix them at a different ratio, and we use the hand layout method to make our composite sample.
Can I ask you, the hemp fabric you purchased as woven fabric, but you are making from scratch the hemp biocarbon as a particulate to add to the resin, true?
Yeah.
Got it. Got it. Beautiful.
Yeah, so this is the company, Ecopoxy. So Biopoxy 36 kit or something. Yeah. So this was the company.
Thank you.
It just says what is the composition.
So it's an eighth of an inch thick, basically. That's 3 millimeters. It's 40 thousandths per millimeter. So it's an eighth of an inch thick, solid laminate. You're not making a sandwich. You're making a laminate. True?
Yeah.
Okay. Was it pseudo-isotropic? When you lay your fabric, were you alternating your fiber directions or just all the same direction?
Yeah, same direction. It was, the fiber was, what do you call that?
Well, it's orthogonal, right? It's orthogonal fiber, right? You got the warp and the weave, but the question was, each ply that you laid down, they were all in the same orientation, or did you have some in 45s?
No, same orientation.
Thank you. Thank you. That clarifies.
So these are just approximate analysis. So we have, even though the goal was mainly on the hemp-based bicarbon, but we also use switchgrass. So
what is that? I've seen somebody else refer to that. Is that just grass?
Yeah, it's just the grass that grows around the roadside. It takes the nutrients from the field and just grows wild.
Thank you.
Yeah, but there are programs now started in Canada where they are growing switchgrass for biofuel application.
Thank
So
you.
there are Agriculture Agri-Food Canada is working on growing switchgrass for for biofuel applications.
Thank you.
I don't want to spend too much time on this one. I can go to.
Yeah, this is probably far more technical than what I'm used to. What he's talking about here is his analysis of it.
Yeah, it's just the biocarbon that we got. So he just analyzing that biocarbon and look at what are the properties of those biocarbons. So yeah, we can, I think, directly go to the results of the moisture and other analysis.
Are you going to be able to send this presentation to me?
We're still trying to publish some of this data, so
Okay.
I can definitely send you the published paper that we have already done on some of this, and that will have most of this data.
I understand. I do not want to steal your thunder. Wait until it's published, but
Yeah.
if you've got published and if you've got previous published articles, research papers, please, we'd love to read more about what you're doing. But continue on. Sorry for interrupting your presentation.
No.
Please continue.
Yeah, so we did the water absorption test. Basically, we created this sample as per the ASTM 570. We dipped them in the water. So weight measurement was done for the 5 weeks. So I think every day we collected the weight to see how much water the sample was absorbing. Yeah, so here, the water uptake, basically, this would be the hemp, I think HAR is the hemp reinforced with the resin without the addition of the biochar in there, or it will be just the resin without any hemp. So, and then after that, the others are different formulation of the hemp. So we definitely saw that by adding the biochar we can reduce the amount of the moisture that is uptake by the composite, and we can also slow down the rate of moisture absorption as well.
Are you speculating that that's because the biochar is hydrophobic?
Yeah. So the way the thing is like because you have a fiber, the natural fiber will have a capillary action.
Yes.
So it will try to draw the water inside. And what we think is that the biochar that is added in between, it breaks that capillary action and provides additional resistance for the moisture to be easily taken up by the natural fibers.
How clever.
Yeah. So okay. And then we also did the swelling test. So and then we also found that the swelling was lower with addition of the biochar. So which also, again, alternatively, it says that the moisture absorption is lower.
On your designations there, the first number 45 as versus 55, 65, is that indicating the percentage of biochar?
Yeah, it was done quite a bit of time. I kind of completely forgot here.
Don't worry about it. It's I'm going to ask a lot of weird. I'm known for asking a lot of weird questions.
No,
we can find out later. It's okay.
Yeah, no, the 10% and 20% is how much biochar mixed with in the composite. So 10% is a 10% biochar mixed in the composite, 20 is a 20%.
And you can
then
see it decline. The swelling declines each time when you go from
yeah,
10 to 20. That's fascinating.
and then I think 50, 100. This could be the two particle size that we are using.
Oh,
And then 445 might represent the 450 °C biochar sample. So that means we produce the biochar at 450 °C
okay. Thank you.
versus 650 °C kind of thing. So we have one at 450, one at 650 °C.
Okay. Thank you.
Yeah, so here we can see that, with 20%, definitely it provides better resistant to moisture uptake. So so this is the flexural modulus before water absorption and after water absorption.
Mhm.
So I think we have some HER. Yeah. So what we have found is like, so we did the mechanical test on after 5 weeks of water absorption, then we did a mechanical test on that sample to see what's the flexure modulus and how the flexure modulus changes. So definitely, when it absorbs the moisture, you are going to see reduced properties, mechanical properties.
Yes.
Here, if you just look at the hemp resin, they have, without before moisture absorption, they are here. After moisture absorption, the properties went down. But interestingly, for the 20% biochar produced at 650 °C, the properties are still above just the hemp resin kind of, composite. So
That's not a
definitely,
small amount either. I'm going to
yeah,
eyeball it and say, are you triple or quadruple flexural modulus?
yeah. So we are looking at
Wow.
somewhere 42 versus 80. So it's a double.
Okay. Wow. That's very impressive.
Yeah. So this also shows that again, it kind of proves the previous observation with the moisture uptake, that if it can reduce the moisture uptake, then it can still retain its mechanical properties, even if it is exposed to water for 5 weeks.
Right. The other aspect that I've seen in a number of the research articles I've read so far, the biochar in the matrix, because it's like a honeycomb, some of the matrix is getting into the cells and it's like a mechanical interlock that
Yeah.
occurs that's so different than, let's say, how do I want to say this? A smooth glass fiber in epoxy is not going to have that mechanical interlock. So
Yeah.
this is a confirmation. Very good.
Yeah. So just yeah, this is just the observation we got. So and now this is looking at the fire properties of the the one
Oh,
of the thing that we want to see is how the addition of biochar can help in reducing the fire propagation and provides more benefit to the fire. And then also look at what is the thermal property of those biochar composite, like the heat transfer coefficient.
yes.
So,
Kind of important in cold zones like Saskatchewan, right?
yeah, yeah. So basically, yeah, because biochar is a very poor conductor of heat, and I think that's what we want to establish. Like by adding biochar, we can further reduce the conductivity, and that might be better for the construction work and all those things.
Yes.
There are other kind of work being done where you further carbonize the biochar and look at that material for electrode application where it
Yes.
will require higher electrical conductivity. But this biochar doesn't seem to have that. It just works as an insulation as we thought. So by adding 20% even 10%, the thermal conductivity was going down. So it was showing that, it can further reduce the thermal conductivity of the material or the composite material. Flame time against the composite. So it just shows like how long it takes for the flame to, I think, to be self-sustained when it is exposed to 10 seconds after fire. Yeah, so again, addition of biochar definitely has a higher time that is needed for the has a much higher time needed. So it's like if you just look at the hemp resin, we're talking about somewhere around 100 seconds to somewhere biochar loaded one, and we're talking about 250 or so seconds. So it just adds another 3 minutes to the calculation. So, and we found we did not get much information about what is the response time for people to react to any fire at home. But there are certain considerations that if you get 2 minutes or something of 2 minutes of warning or something to run away, then that can be a great addition, or that can greatly help. So definitely it does shows that it can improve that fire retardant properties.
That's very good. And for me, it's been kind of anti-intuitive because I would have thought pure carbon would be easy to ignite. And yet you're showing, and I've read this in other papers, that it is actually a flame retardant. So
Yeah.
Thank you.
Yeah, the reason why that is true is because most of the resins that is used like for the sidings and all those things at home, these resins, they burn around 100, I do not know, somewhere between 60 to 100 degrees C when they get the flame, right? And most of these biochar, they are produced at around 400 degrees C, so they are kind of thermally stable up to that up to that temperature,
Yeah,
at least.
I
So
get
that's
it.
the reason like why it kind of helps to improve that thermal stability of the composite.
Thank you for that explanation. It never would have occurred to me. And I
Yeah,
hadn't read it yet, so that makes sense.
and
We
it's
have
just
something similar
when
with a lot of our epoxies for aircraft or spacecraft. You're processing temperature for it. You lock it into place, right? It interlocks and it is less. It is quite resistant up until that temperature, because
yeah,
that was
and
the
it's
cure
also
temperature. Go ahead.
yeah. And it's, yeah, as you said, the epoxy, like the idea is when you add a biochar to it, then it just tries to break that propagation of fire through it, so that delays the overall fire action or something. So
Very good.
so yeah, we did see there is you know there is benefit of adding biochar into composite for thermal and fire retardant application. And then we looked at the mechanical properties of these composites. Yeah, so we looked at the effect of temperature, so 450, 550, 650. So what we found is, the one that are carbonized around 550 gives the maximum tensile strength. Similarly, particle size 50, 75, 100, 50, 75 or something similar, but if you go larger particle size for the bicarbon, its mechanical properties goes down. And that's, the dispersion is the main problem. Like when you have a larger particle size inside the resin, that hardens very quickly. It is a big challenge that how do you mix it so quickly that you get proper dispersion before it gets hardened. So that's one of the challenge when that we faced during while making this sample.
Interesting.
Yeah, so these are some of the samples that we tested. Again, the flexural modulus gets higher at 650 because it gets very brittle when we take the 651 and use that. Similarly, 100, it gets very brittle. So, Yeah, 10, 15, 20. The 20 gives a higher Fleischer modulus.
Very good.
So the impact test, again, this is, yeah, we found that 551 has a lower impact or requires a lower impact energy as compared to 450 and 650. In this is something that we're still trying to understand what is happening there.
Interesting.
Yeah, with that 550 biochar. So yeah, so when we compare the properties of the material that we got, we found that the specific tensile strength, it falls within that within a range of these glass fiber reinforced composite materials, in between that glass fiber reinforced composite.
So it's almost a direct, mechanically, almost a direct substitute. Is that what you're starting to feel like that's what you've got here?
Yeah.
Wow, that is impressive.
Lies in between, the glass fiber reinforced, the unidirectional thermosets. They can range from somewhere between 350 all the way to 950. And we were somewhere around 630, 640. So it's in between there. So we can, yeah.
Impressive.
Yeah, so we found that the optimum condition could be 650, 20% loading, 100 micrometer biochar, 100 microns biochar size could be an ideal for this kind of composite application. Yeah, so
very impressive. And your 20% loading, is that 20% of the weight of the entire face sheet? I want to make sure I understand that term. 20% of the total weight?
Yeah, 20% of the total weight.
Okay, so whatever it weighs, 20% is the way,
Right.
Of course, we're looking at it for carbon sequestration is 20% of the weight is totally locked up for very, very long periods of time, depending on how long the epoxy lasts. But let's say that you complete using it. The ones that we're talking about for these shelters are maybe a 10-year lifespan, at the end of which they just go landfill, which probably is a good thing for these. So you're sequestering the carbon maybe forever in these epoxies in the ground forever. And so what do you think?
The other thing that can be done is after the use, you can chop it up and use for energy applications because it will have a much higher heating value. If you are working with the bioepoxy, then, the impact on the environment would be less. And then you fill with the biochar and, organic fibers that has a high energy value as well.
Okay.
So you can, break it down into fuel.
Very good.
Yeah,
I totally appreciate you me walking through this presentation. How would you like to proceed, if at all, in working with us? Is it a case where you want to stay with your research, and if we use your research in an application, that's just basically our business, or do you want to engage with us in a form of, say, joint venture or partnership? You don't have to answer instantaneously, but please think about that, because we are looking actively for partners and ways that we can move from research to applications that benefit humanity. So have you thought about that at all?
Yeah, normally, the way we interact with the industry's partner is basically either that could be a research project or the contract project or something that we can help to, if let's say we're talking about flax and the shibs is used for biocarbon, and producing biocarbon-based composites, doing the characterization of that. Those data, I think, would be a valuable data, right, for you to consider for your application.
Sure.
Yeah, so we can definitely kind of help in that area, and the funds can be either contract funds from the industry that can support the student and the other operating cost for it.
Okay.
or whichever way we can support that work. So
Yeah. By the way I'm looking at it and the way we are starting to approach it is you can see the US, Canada, and UAE are talking about investing billions of dollars in carbon capture projects. And obviously, none of us are interested in billion-dollar projects. We're interested in small amounts for a niche application. And so what I'd be doing is I'd be trying to convince certain governments to invest in this research and this development. Now, on the other hand, we do want to connect up to pallet shelters and see if they are interested in, for example, using some of these composites panels as a prototype for a different version of their pallet shelters. They've got the one that's the standard fiberglass, and then maybe we make a few prototypes out of bioplastics, biochar, and what everybody would want to do is build a few and then test them to see, are they durable? Do they work well? Do they off gas? Do they have weird reactions to weather, UV, etc.? So some practical real world applications. So I'm certainly not coming to you asking you, do you have funds to work on what we have in mind? You have the technical expertise that we do not in biomaterials. And so we're looking for that sort of contribution. And we would never expect you to be able to do it for free, right? You've got the equipment, you got the test, you got the knowledge. So part of whatever funding I was able to gather together, part of that would be for your lab and your work. The other question would be, would you like me to work directly with you? Or would you prefer that I work with any of your postdoc or PhD or undergrad students? That's your decision. How would you like to, would you like me to go away for a month or two because you're busy and the holidays are coming up? Or what is your zone of engagement right now, my friend?
yeah, so I can definitely be have a discussion with you whenever needed. Right now we don't I have students working on different projects, like including with the Titan. We have a project with them, and they're is working on that project. So I don't want to kind of divert their mind.
No.
So we can have a chat, and then whenever you need some information, you let me know.
Okay.
But I just want to let you know that I'm traveling from next week, and we'll be back on January 12th. So I'll have access to internet, so definitely, if there is anything, I can share information with you.
Okay.
Yeah.
I have a single request then, that you send the one research paper that you've got from previous that you'd like us to take a look at. And I hope that you enjoy your holidays. This was a great start. I am looking at this as a very long-term commitment. I'm not trying to build up a product in a few months, okay? Yeah. This is a long-term effort for the entire planet. So thank you very much for your time today. This is very encouraging. The work that you guys are doing is very encouraging. I'm very happy. Thank you so much.
Thank you. Thank you, Mike. So
bye, Bishnu.
Yeah. Have a good day.
You too.